Thank you very much, and I would like to thank the organizer for inviting me to present our current work. And basically, this work done mostly by my postdoc and diploma students, Alexey and Artem Nasenko, and we just trying to get what are the low energy metastable state in these dichalcogenides, which is basically also van der Waals materials. So basically van der Waals materials and this region started to be very interesting because of the graphene, that we can mechanically make various structures, and by either mechanically or chemically, and we can control basically this structure. There are a lot of different materials. I would just say what I want to present. First of all, of course, very close to what we have in graphene are dichalcogenides. Here we have very similar structure, similar, boron nitride. So here, for instance, boron nitride, we have boron and nitride, which are forming hexagonal structure. The same type we have in dichalcogenides, that this is a very two-dimensional material, and you can quite easily to split. There are two, this is the main families which we investigate in van der Waals. As I told that dichalcogenides, also phosphorine and other materials, and was presented again. This is not dichalcogenides, but this is more complicated structure, which was presented by previous speaker. So I will, and if you consider all these materials, in principle, we can have two types. We can have insulator, like here. This is this magnetic insulator, but also we can have different type of the semi-metals. And in particular, the richest life is in dichalcogenides, because there are a lot of different dichalcogenides, and some of them are basically like here. We see a very big gap semiconductors, but some of them from this group can be also semi-metals. So, and there are two types of main type. Okay, good. And dichalcogenides basically dichalcogenides basically we define that we have transition metals. Usually we are considered 3D transition metals, and also two halogen atoms, which are basically sulfur, selenium, and tellur. And there are also dichalcogenides which is also with 5D elements, but basically I will speak only on one very small family on titanium. So the characteristic feature of dichalcogenides, there are two different structures, and therefore it's very important, and the same compounds can be in two different structures. This is in trigonal, with trigonal symmetry, which is presented here, and basically one means that it repeats itself in one layer, and in two layers, this is 2H structure, which is hexagonal, has hexagonal symmetry. And usually, most of the structures, if we can see, this is the present what we know, and basically these materials were investigated a lot in the 70s, and we know about a lot about these properties of this material. Nevertheless, we find new and new experiments. And basically, if you can see that from this table that most of these materials can be presented in both form, hexagonal and trigonal. And here, star means that they can be metallic type, or this is 2-star in the semiconductors type. So, and I will speak about this series, which is basically presented as a trigonal symmetry semi-metal type. Interest the most interesting here is titanium diselenide, basically because, first of all, of course, if you look to the structure, it's a layered material like we know cuprates and iron arsenide. Therefore, first it was investigated as a material where we have superconductivity. And superconductivity material very similar what we have basically in cuprates or iron-based superconductors. That was 2011. Basically, already after 30 years of knowing these compounds, people decided to intercalate these materials and to see what happens. So, what is similarity in all these cuprates? The parent and iron-based superconductors, the parent compounds are magnetic. And then if we dope or apply pressure, basically this magnetism goes away and we have room for superconductivity. And exactly the same we have for charge density wave, which appears in titanium diselenide. If we apply, if we intercalate by copper, charge density wave goes away and we have superconductivity. Therefore, it was interesting just to investigate what is the reason of superconductivity and what kind of superconductivity we have in this case. Because it's very similar what we have in high temperature superconductors. So, for me right now, the most interesting, this is the same as in cuprates, the normal state properties. So basically, it's even much more mysterious than this charge density wave than superconductivity itself, at least from the first point of view. So how do we see that charge density wave? Basically, if we consider pristine compound and consider superconductivity, temperature dependence, that then it goes more or less as semiconductors type up to some have a peak, and this peak corresponds to charge density wave transition. That was the first how people found this. Charge density wave is the following structure. In principle, this is a structural transition, what we see in X-ray. That here we have the structure where I have only titanium atoms, two-dimensional titanium atoms. And the transition or charge density wave is basically we see like a shift of the free atoms around one central towards this central atom. And we have basically this structure. And also because we have restructuring, we see the same in ARPES, and ARPES basically at high temperature, and we see two pockets close to the Fermi surface. One at gamma point, hole-like pocket, and electron-like pocket around M point. And if below this transition we have restructuring, first of all we see the opening the gap at gamma point, and also we have we see the folding of this gap which coming from the M point. This is very small. So this is the evidence that we have really charge density wave. And also the second experiment, also quite interesting, was done with STM, measuring what kind of the charge density wave happens near to the surface. So this group say that the following, that in principle, STM is sensitive not only to the very last layer, but also the next one and after the next one. And they found 3 different domains, and in each domain, they see charge density wave which happens in one of the direction. Altogether, this is triple Q charge density wave. Just for description of this charge density wave, we need simultaneously three vectors, which is 120 degrees to each other. So, and recently there was additional experiment, which in point contact experiment in our institute. Point contact spectroscopy is the following. Basically, we take a very thin tip just to the surface and measuring resistance in this case. Usually, okay, I just showed the usual picture, what was expected and why people are interested in this. One can get information of electron-boson coupling in this case as the second derivative of the voltage over the current. So, and this value, the second derivative, is directly, one can show that in this case it's directly proportional to the electron phonon coupling alpha quadrat f. And basically that was the main motivation for this investigation, just to see how strong is electron phonon coupling. So, and this is typical what was done, for instance, for iron-based superconductors with copper point contact, and we see that the strongest is at 20 millielectron volt, and if you look the bosons there, basically one can see that it basically corresponds to bosonic type, namely with this peak, and that was the reason. But in addition, what was found is quite interesting, that if we are starting here, and this is resistance, the first derivative of the voltage over I. And what was interesting, that if we apply this voltage, it's a metallic state, it's quite small resistance. The resistance is of this point contact is about 10 ohm. And it's different. It depends how you prepare this contact, and every time you can, this is a little bit uncontrollable process, but nevertheless, if you are doing statistic over 100 different point contacts, you can get the following. So if you apply the voltage, basically it's reversible. If you increase with applying the voltage, you have increasing of the resistivity. There are several reasons of the increasing of resistivity. As I told, the first, this is because increasing of the response of the electron phonon coupling, backscattering at the point contact. The second, because of the thermal effect. But nevertheless, if the voltage is quite small, below some threshold, we always have the same properties and go along the same line. But if we increase above, and in this case about 1 volt, then we are going to completely different curve. And this is semiconductor type of this curve. So basically, and we will stay forever at this basically semiconductor state. Something like, okay, I'm saying something like semiconductor, but definitely this is exactly what people see in semiconductors, this type of the behavior of resistance versus the voltage. And what is interesting, applying to the opposite direction, we're switching back to this low resistance state, and can stay here. So this is like a switchable effect, which is which appear because of the response to the current. So, and what is interesting, that it survives up to the room temperature. Of course, it becomes less pronounced. Here you see this is 2.5 Kelvin, and at very low, this is the black curve, and the blue one is at room temperature. And the threshold becomes smaller and smaller. Similar effect was observed also in some Waals semimetals like tungsten telluride and molybdenum telluride, which are basically also van der Waals materials, late materials. So, and this is one of the reasons of our investigation, just to see if we have some low energy metastable state which, to which we can switch our material by the current or electric field. The second, also, we were quite curious why in the case of titanium diselenide we have charge density wave, which basically goes away with the pressure. But if you look titanium ditelluride, which is basically isovalent, we have no charge density wave. If you look just a simple picture, band structure calculation, GGA, we see that there is no so big difference between all this material, titanium from band structure, electronic band structure to point of view, titanium sulfur, titanium diselenide, titanium ditelluride. Basically, this is free colors. So in all these cases, we have around gamma point, we have hole-like pockets and electron-like pockets around L point. So basically, in all these materials, we have so-called nesting when we have similar by the volume electron and hole-like and electron-like pockets, which are shifted by some vector q. And this is for very long time was considered like the main idea behind of this material. Basically, there are several theories which try to explain what is the origin of charge density wave. One is just phonon condensation. This is just a normal structural transition, because in the structural transition, what we have some structure at low temperature, then increasing temperature give you motion of the molecules. Therefore, because of this entropy, another structure may be more preferable. So, but most of the theory are coming from electronic mechanism. This is either excitonic band. They are very similar and very similar by idea that we win some energy because opening the gap. So excitonic band Young-Taylor instability, also orbital order or interpel, more complicated mechanism for this charge density wave. And basically the idea is the following: if we have some whole band around gamma point, electron band around L point, then we can win energy if they open this gap in both cases. And basically, this is because we have nesting between this point, and energy of the quasi-particle is equals minus energy, so electron hole, and then we have airplane instability, divergence of susceptibility, and so on, and we have either spin density or charge density wave depending on the interaction. So, what we did? We decided to look, first of all, if we can consider of all energy structures. So basically, we are saying the following, that let us take several atoms and predict what kind of the structure can exist in this case. And considering not only the ground state, but the lowest metastable states. So we are saying that let us put in some volume 5 atoms, 3 of them titanium, 2 of them selenium, and just look what will be the energy. This is, we use so-called evolutionary algorithm. It means that we are putting the first structure and calculating the energy. After that, making a different movement, shifting of the a little bit atoms by some algorithm. flipping, and so on. And basically, what we are doing, we are considering some multidimensional space of the energy. So basically, depending on the distance of the titanium and selenide. So basically, of course, it can be mountains, it can be basically some low energy states, and we are looking and trying to find, and we have many different local minima, like here, and then we want to calculate all the local minima. It means that in principle, the system can exist in this local minima as long, very long time, until it can go to the ground state, at least at low temperature. And if we consider everything, we can consider if it's possible to have semiconductor state with low energy, and if we can have the transition. So basically, the idea is I told that we have some ratio of titanium and selenium, and then calculating with this number of the atoms all the possible structure, and after that relaxing all these structures. So, and also we calculated some triple states like selenium, titanium, and sulfur, and tellur. Okay, but I will speak about basically titanium diselenide and titanium ditelluride. Okay, there are some technical issues with all the dichalcogenides and basically all the material van der Waals materials, because of the large distance and because of the van der Waals forces, that you need some correction for these van der Waals forces in the calculation what we use, and basically this is the result. So this is the result for titanium diselenide and titanium ditelluride. What we see? So in principle, at high temperature, the ground state has the symmetry, the space symmetry 164. This is the zero energy. This is what we name disordered state. So, and the state, with charge density wave, it's not even present here because it's higher by energy. So, and we see that in the case titanium diselenide, we have a lot of different minima with this type of symmetry, and this is lattice constant. And basically, all they are even smaller by energy than this is trigonal 1T structure, and they are lower a lot of, and basically they can be explained in the terms of different type of charge density wave. That was the main point, and investigate if you have semiconductor state. So, in the case of titanium ditelluride, we see that the lower state is this 164. This is exactly disordered state, and no low energy metastable state. Basically, already what I want to say, that already on the level of the Coulomb interaction, the material have the preference towards of the charge density or spin density wave. And by this calculation, we can say that if it will be there is instability towards charge density wave. This is distortion which can be presented in this case, how to present the structure. So this is can be single Q, double Q structure, and triple Q structures. So basically, we haven't found any good basically semiconductor state. The best one is presented here, but nevertheless we didn't find. it means the mechanism probably is not just transition to another, but this also vacancies and interstitial atoms are very important. So we saw, okay, let me skip this as quite, so we saw, okay, sorry. We saw basically that, yes, there are some states with quite low density of states, but this is not in reality a gap or very small gap. And also, okay, this is, and this basically also can be explained because of the all this state which is moving of the atoms can be explained by various vector of the nesting between these pockets. And if we find, so basically we find everything in coordinate space and in the momentum space, we could find corresponding interaction between different pockets. And okay, let me skip and come to the conclusion. Basically, what we found that basically the already on the level of DFT, the materials with okay, very similar materials, isovalent materials, with already on the level of DFT, we see that they are very different. So some of them basically can have metastable state, some of them do not have a metastable state. And this probably, if we include multi-particle physics, it will give us a true triple Q state, which we see in the experiment. That's all what I wanted to say. Thanks.
Thank you very much. And your question, please. I have a question. You talked about theoretical prediction, some stable, stable structure for this compound, and exists some experimental with experiment, this prediction and experiment. This is
so in principle, not for titanium diselenide, it was quite much investigated. I know that there are several compounds which already were using this technique. First was predicted and after that found in the experiment, especially at high pressure. This is nitrides or iron nitrides and some other nitrides, which first were predicted and after that found the experiment. This is a new technique which is just growing because of the computer time it needs a lot.
Thank you.
So do you observe some clear trend on the role of the spin-orbit coupling for the charge density wave instability? For instance, if you go from sulfur to selenium and tellurium based systems, does it play any role?
No, we do not see any role.
That is surprising.
It's surprising. So basically, if I compare titanium sulfur and titanium diselenide, there is almost no difference. I have, for both of them, a lot of metastable states. There are already a big difference between sulfur and selenium, but we do not see. So this is something which is okay. This is something because of the small, very small pockets in titanium diselenide and much larger pockets in titanium ditelluride. So here, the closest to the Lifshitz transition, when they disappear, it's very important. Whereas the optimal, unfortunately, right now we cannot say. This is still investigation because we have only 3 materials which we can compare. That was our first question about orbital, but we can calculate this as with orbit, without orbit. Okay, there is a little bit difference, but titanium ditelluride is very different from titanium diselenide.
Okay, if question is absent, Now, thanks, Peter, again.